Welcome to James. It's great to have James here. And James is currently an assistant professor at the Department of Psychiatry and Biostat at University of Pittsburgh. And he is an expert in network data analysis. And in this talk, he will describe some of his recent work. So let's welcome him. And I have made James as co-host, so I'll mute, and it's all yours, James.
Thank you. Thank you so much. And thank you for inviting me to this, to give the talk. I actually wanted to come by to see the campus. I was nearby in the Bay Area, so took a drive down here, and it's a beautiful place to be. You guys have a really nice building and surrounding redwoods everywhere. It's definitely a nice little haven to be doing research, doing statistical research. So thanks for having me. And actually, that's what was going on at the beginning as we were figuring out how to not have echoes. So now I think we've sorted that out. Thank you, Robert, for letting me use your office. So great. So today, I'm going to talk about network representation. And in particular, I'm going to look at this from a very well understood and well utilized strategy of principal component analysis. And so let me actually get started with this. So can everybody see my screen? Just making sure it's large enough. Okay, perfect. So a little bit about me. So I received my PhD in statistics and operations research from UNC Chapel Hill. So I put in there, go Hills. I know they didn't win the championship, but they did pretty well this year, going to the final. For those Duke fans, I'm sorry. I was before, so I then went directly from UNC to University of San Francisco, so USF, where I was an assistant and then promoted to associate professor there for the last 6 years. And currently I'm an assistant professor of psychiatry and biostatistics at the University of Pittsburgh. My focus has been, and you'll see more on this, largely to understand how networks play a role and understanding social dynamics, neurobiological systems, behavior, and neurodegenerative disease. And before that, I should mention, I didn't put it on here. I went to Clemson University for my master's in mathematical sciences, and I know Robert Lund from back in those days in 2008. So this is, I have a connection to your department, and Robert, thanks for putting my name out there to get me to give a talk. So my research interests in general are kind of in three main veins. So one is really network modeling and analysis of what's called functional connectivity. And I'll spend more time on that. But the essential idea is how to use and develop network models to capture connectivity patterns of the brain and how this relates now to behavior, aging, and disease. Another research interest, which I won't be talking about much here, but I'll just mention it, is really understanding and analyzing dynamics and change of time varying networks. So here, I'm very interested more so from the tech side of things. So looking at social media and understanding how to identify influencers and assessing their effects on information dissemination, as well as sentiment and emotion in users on social media, but also in detecting change in social behavior and interactions because of, but also, independent of these influencers. And then third, I like to put as kind of a large theme of interpretable machine learning on networks. Some people may argue that statistics is just interpretable machine learning. I somewhat agree with that. There are a lot of nuances to these kind of black box methods that I think have very strong ties to other, main theory that we know, probability theory, as well as a lot of laws in linear algebra that we can bring all of this back to. And using mathematical forte and these kind of the skills that we statisticians have, we can really bring a lot of understanding and inference to otherwise black box methods. And so hopefully you'll get a picture of that once I'm done with this talk. So from an application standpoint today, the method I'm going to present is general to network data, to samples of network data. But really what I was motivated by was thinking about samples of networks from functional imaging with functional magnetic resonance imaging machines, so fMRI. And the typical idea here's an example of an fMRI machine. A person is put in the machine and asked to stay at rest or perform a task. And these tasks are often created to kind of activate certain parts of your brain to see how they react and how this differs across different populations. And what's measured is blood oxygen level dependence are taken over time. So you have this magnetic scanner that's essentially measuring the volume of oxygen level response in each region of the brain across many different slices of the brain. So in particular, what you have are these three-dimensional objects of the brain from a scan that's occurring continuously, and you're observing this through time. So the way that we typically view this is thinking about voxels, which put simply are three-dimensional pixels, right? So we're imagining these kind of cubes of the brain where we observe a time series for each one of these voxels over time for as long as they're under the machine. And so these data are very noisy, and it's high dimensional. In the case that actually with high resolution scanners, we often have up to 1 million different voxels that we're recording at the same time. And these trajectories, the time series themselves, are dependent both anatomically, so based on actual physical space in your brain, and functionally, so how they activate at varying times. And so network modeling of functional connectivity in a very basic schematic is really doing the following. We're getting fMRI snapshots, which these are actually three-dimensional, and we're viewing these over time. You can imagine taking these snapshots and essentially mapping them to voxels, where then we view voxels over time. And we get a single time series for every voxel. And so we can view this as an incredibly large multivariate time series where there is necessarily dependencies between these time series. And from that, we essentially want to take this multivariate time series and assess some form of dependence between each voxel to get what we call a functional network. So when someone talks about a functional connectivity network, they're really talking about what are the activation level responses. So these are the oxygen levels that we're recording over time, and the relationship between two voxels, right? So in this case, every node represents either a voxel, or you could bring that, spatially to something called an ROI, a region of interest. And edges between them are just strengths between the time series that we observed from the data itself. And so that's in general what I think about. There's a lot of interesting research on saying, when we talk about co-activations, what's the best strategy for actually assessing dependence between these variables? I mean, there's a lot of options there. Correlations are by and large the most commonly used. Doesn't mean it's the best in the world. I mean, there's a lot of caveats and issues that can happen with correlation analysis, but but other types of similarity measures you can imagine could be used here as well. And I actually want to stop for a second and say, please do stop me if you have any questions along the way. I'm happy to interact and answer questions as you have them. So far, are we good? Perfect. So why network analysis? I'm actually drawn to this. I really enjoy this picture because I think this picture tells us a lot about what network analysis can honestly offer. So this is actually thought to be the very first image of a network that was really drawn to try to analyze a social system. And so it's from the 1930s by a psychiatrist named Jacob Morano. And what it's drawing is actually friendship patterns between children in an elementary school. And so what we actually have, it was drawn in a nice way where basically triangles represented boys, circles represented girls, and there were directed edges between them. So you can barely see the little arrow at the end of this edge, for example, but directed edges between nodes where a node points to another node if the origin node said that the other person that they're pointing to was their friend. So it's kind of a nomination scheme. So what's interesting about this, and I think what's so telling about network analysis, is you can gain a lot from this visual just by about this class. You can gain a lot about this class just from looking at this picture. For example, well, actually, what do you see to begin with, just to make sure everybody's getting into network analysis as much as I am? So what's something you notice between boys and girls?
Well, girls are being friends with girls and boys with boys.
Exactly. Boys with boys, girls with girls, except for this one person who thought he was friends with a girl on the other side. Yet the interesting thing here is she did not reciprocate that tie. Right? So he nominated her, but she's like, nah, she only nominated other girls. So in general, there's clustering or community structure, right? So based on boys are more, are saying they're friends with themselves. Girls are saying they're friends with themselves. And then another thing to notice is the fact that there's this kind of pair right up at the top that are mutual. So they're friends with each other, but they're not really interacting with the rest of the class. And so a lot of what happens in network analysis is this type of analysis, just now at a large scale. So we try to make inference like this, these basic findings that we can see in this picture, to a larger scale to say, well, can we say something about community structure in general? Can we say something about, single pairs of individuals or of nodes? And what does that mean in correspondence to the system that we're modeling? So why network analysis for the brain? Well, from that picture, networks provide interpretable models for complex interactions. So when there's interacting systems, when there's dependent data, it's natural to use a network to model these kinds of data. And in many situations, classical inference does not capture the dependencies between these regions. So we can't assume the same kind of independence that we usually do with a lot of multivariate inference. And not only that, but network analysis has been used in the last about 15 years for fMRI kind of data. And it's really helped the understanding of the general organization of the brain, of understanding different processes of the brain, as well as information transferal and integration of information. But today I'm going to take this a little bit further and focus on actually population analyses via network representation learning. And so the idea here is we don't just have one network, but rather we have many networks. And in fact, we're considering a sample of networks where each network is a single observation from a population. And in functional connectivity, what we think about are scans, for example, over individuals with similar characteristics. So you may have a group of people that are considered healthy controls versus another group of people that have been diagnosed with ADHD. And so we'd like to know, okay, we have a sample of healthy controls, a sample of ADHD. How can we go about comparing these two? Or how do we even analyze these samples in the first place? And then another way that you could view this is actually multiple scans for one individual. So if the individual came in multiple times, so had a longitudinal study, for example, or had repeat scans, or had multiple different types of imaging scans on the same individual. In each one of these cases, we have a sample of graphs that we need to analyze instead of just one. Challenges are that the data observations are high dimensional independent. And a really big challenge is what features of these networks do we care about? And I think this is really an underlying problem of network analysis from the get-go, is what features should we analyze? It's not an easy question, and I think that's always going to be up for grabs, and that's sort of a modeling question of what really matters, and I think it also is application-driven. But one thing that network representation learning, which is what I'll be focusing on today, tries to do is to identify useful features, right? And so in particular, it enables multivariate inference for complex networks, including downstream machine learning tasks. And so put very simply, it's, as we know, obtaining low-dimensional representations of a graph. That's really what network representation learning is trying to do. And in particular, the aim is to identify continuous features of complex networks that are easy to use for future machine learning tasks or statistical inference tasks, like prediction, classification, within network clustering, et cetera. For a sample of networks, instead of just a single graph, like in this picture, what we have instead is actually a sequence of graphs. Let's call it G(m). So you can imagine you have a sequence of graphs or a collection of graphs, G1 through Gm. And suppose that we let capital N here be the set of unique nodes in this collection of graphs. Then the aim is to learn an interpretable low-dimensional feature representation of the regions N, namely a d-dimensional representation, F, which are called embeddings, or the representation of the network. And here, when we look at nodes in particular, the jth row of F is just what is sometimes called the functional embedding of region J across the population. So functional embedding for functional connectivity. On the other hand, again, this can be used across many different types of applications. I just like to think about this in terms of functional connectivity. One thing I want to point out, though, so this is kind of the typical strategy for network representation learning, and there's a big literature. There's a very large and vast literature in computer science that have looked into methods and developed methods and algorithms for answering this kind of question. One thing that I want to point out, and I don't think this has really been noticed or investigated yet in the computer science literature, is that network representation learning doesn't have to be at the node level. So we don't have to take this and say we need a feature for every node. And in particular, it can be defined for any subsets of nodes in the network. And so I'll offer a few kind of past or contemporary methods that are currently used, maybe the most famous types that have been developed recently. And some are what I'll call descriptive methods. These are fast and often very predictive summaries of the network. Examples include recent examples like deep walk, the line algorithm, node to vec, and variants of node to vec. For those that have, maybe you've heard of word to vec before. So there's a really big natural language processing problem that Google introduced, or an algorithm called word to vec that Google introduced, whose point was to basically understand similarities between words. Node to vec, and you'll see a lot of, once you start Googling these things, a lot of to vec names of algorithms. So it's simply taking the graph and trying to understand similarities in latent space between nodes. So incredibly popular methods that are widely used, especially in tech that I've seen, and then also within academic research. And the strengths make sense. It's computationally fast. So these kinds of methods are really used for incredibly large graphs. And social media, sometimes nodes up to millions, and it can be done in minutes, right? So these algorithms can be applied in minutes. They're scalable, they're predictive of network classes, so very predictive, and offer insights into the community structure of a network as well. The weaknesses, though, so they're predictive, but inference is harder. So the identified features are not directly related to structures that we can interpret. There is some work in trying to to add some interpretability behind these features. And some recent work has come a long way, especially in deep learning and these kinds of algorithms that are being developed. However, I still would say, the approximations that we're getting out of this are still not understood enough to where we can make, nice interpretable and clean inference out of the features that we identify. For example, it's recently been shown to these kinds of methods, node to vec variants, to not be capable of actually capturing triangle structure in a graph. And so this is a very common type of structure that people wish to capture in a network to understand kind of clustering in the network. So the clustering coefficient, for example. Another way of going about these embeddings or representation learning is through model-based methods. So the focus here is on describing the generative process of the network with probability models. So this is very much more in line with statistical inference. And examples here include the latent space model, the ERGM, so the exponential random graph model, the dot product model, to name a few. The strength here is that they're interpretable, and they provide an understanding of parts of, anyway, the generative process of the network. Weaknesses, they're often slow and not scalable. So for large graphs in the order of millions, most of these methods rely on some form of MCMC or a variant. It becomes nearly impossible to use these kinds of methods in real time. And so they're also not typically as predictive as their counterpart, though that's not necessarily a weakness. It just depends on your goal. And one thing, and this is actually what brought me to this literature in the first place and really thinking about it, is that often the features that are incorporated in these models, so the covariates, so in a standard regression that we would use, and these kinds of models are often very highly correlated. And that correlation is not taken into account with these styles of models that we currently run. So how can we fix this kind of problem? And also I'm going to add to it by doing it not just for a single network. So methods to date provide node-based, usually not interpretable representations of a single network. Here, we're interested in subgraph representations for a sample of networks. So I hope to introduce an interpretable framework for representing a sample of networks. And I'm going to use network subgraph counts to characterize the sample. And then I'll analyze the large sample properties of the method. And in particular, I introduce what I call the PCAN and I am from North Carolina, so I call this the PCAN algorithm. You can call it pecan if you'd like, but I finally got an opportunity to add a little bit of Southern twang here. But anyway, PCA for network samples in particular, algorithm to identify subgraph representation for a sample of networks. And the overview idea here is to use subgraph densities to characterize the sample, apply PCA to the subgraph densities of the sample, and then analyze the large sample properties of the method. So let me give a few. And this is overly formal. I put it here in case you want to read the details, but by all means, let me explain. So essentially what we do, actually, maybe I can just put it in a picture. Essentially what we want to do is describe this sample of networks with subgraph counts, and in particular, actually subgraph density. So we're going to be looking at the ratio of how many configurations we see to how many are possible. And so some examples that we'd like to see, for example, are anything you can draw that would be a subgraph within a network that you're trying to analyze. So you can imagine, for example, edges are just a single 1 star. So we have a connection between I and J. You can imagine 2 stars where you have now a central node J and it's connected to two other nodes, hence 2 star. And you can imagine this being broadened to 3 star, 4 star, and so on. Triangles, so there's our triangle structure, and further cycles, right? So you can imagine 4 cycles, 5 cycles, and so on. And the list goes on. So basically, why would we care about these kinds of structures? One, they're highly interpretable. And if you can draw it, we can count it. So the idea is in social dynamics, these types of structures have interpretation. In the brain, they have interpretation. And there's a lot of really great work on understanding what it means to have varying extents of these subgraph configurations within your network. They're commonly used as descriptive statistics for networks. It's kind of the first step is saying, well, I have a lot of networks that I want to analyze. How do I know where the differences lie in the networks? Let's calculate a lot of statistics like this. So we can think of them as summary statistics and compare across the populations. The interesting thing is that by and large, folks will look at the mean differences, especially, from what I've seen in a lot of the applications of these kinds of methods. They'll do mean differences between these subgraph counts and kind of stop there. Right? Not so much counting for the variability within network statistics as well. Moreover, and what is really interesting here is that there are also sufficient statistics for a large family of models, including the ergom, as well as, and I'll talk more about this, the kernel-based random graph model. So this was just putting that more formally, but you can imagine instead of specifically counts, we're going to be looking at, I just want to point this out, these S tildes, where if you define a configuration F that can be drawn, then we're going to count within a graph the number of times that configuration occurs. And that's our SF of G. And if you let MF of G just be the maximum number of times it could have happened in the graph, then what we're going to look at is actually the density, which is just the overall counts that we saw divided by the total number of times it could have happened. So just the ratio of the occurrence, basically the occurrence of that given statistic, our configuration. And once you have this, and this, so I should also say, and maybe I should have put this when I said a little bit about me, I like to keep things as simple as possible to still get something useful out of it. So now if you imagine you have these summary statistics, and you believe that there are enough information in these summary statistics to kind of quantify or to characterize the networks of interest, then what we can do is to now try to run something like principal component analysis on network samples simply by doing the following. So if you just select now a collection of subgraph configurations, so say that's bold F, so you choose P of them. And in this is manually selected. This would be something that someone would choose. I can talk about later how would you go about choosing these. I think the point is, as long as P is not too large, it's okay to try any suite of statistics you would like to look at for understanding PCA. And an example here, imagine we wanted to count the 2 stars, the triangles, and the squares, or the 4 cycles in the network. Then for each network GJ, you're going to get the count statistic for that given feature, right? So for every feature, we just count it. And then we normalize the accounts according to the density, so just the ratio of observed to possible, construct the subgraph density matrix, I'll call it bold F, which is just looking at these counts across. So this is the P by capital N, where N now is the number of graphs in the sample. So we have a P by N matrix, which I'll call the subgraph density matrix, and apply multivariate PCA on the columns of S. So put more specifically, this is running PCA on now the variance covariance matrix associated, or running a decomposition on the variance covariance matrix of the matrix associated with these sample statistics. And the interpretation is nice, and this is something that is well understood in PCA. So I'm not saying much here that's beyond what we already know, except actually in networks, when we're thinking about networks, this kind of analysis has not been done. So with all of the analysis that has been done for embeddings and network representation theory, there has not been something to say, what can we say about our features at the end of it? Like, here's our output features. What can we say about it? So the real thing that I want to point out that I think is very valuable here and deserves more attention is really point 3, which is essentially if you were to give me features, so the PCs from a network sample, instead of the network sample itself, we can get the best reconstruction of the sample statistics for any configuration by using this approximation, right? So we'll get the approximation for what this density should be for graph I that is closest in Euclidean distance is just given by the following dot product, right? So here we're just taking the PCs to reconstruct the graph in a way. This is valuable for a lot of reasons. In many cases, especially when we're thinking about social networks, it's often the case that you would like to run an analysis and convey the information in a de-anonymized way or in an anonymized way, where you don't understand any of the features per se of the person or an individual information. So this allows us a way of saying we can communicate information using the PCs from these graphs and still get the closest approximation to these summary statistics that we'd like. Now, something else is interesting about this is these summary statistics, as I said, are sufficient statistics for a whole group of network modeling or network probability models that we can use. And so networks with these statistics can be simulated, and then inference can be drawn from that. So there's a lot of interesting things that we can use with this best approximation, and that's certainly something I'm going to look into more in the future and deserves more attention. So that's just a quick comment. So now I gave you a simple method for running PCA on networks. The weakness, and I'll have to admit computational weakness here of the PCAN algorithm, is that actually it can be incredibly slow on large networks. So if you have networks on the order of millions of nodes, it would take a very long time to run this algorithm. And in particular, this is primarily due to the fact that we have to calculate network counts or subnetwork counts. And so as an example, if you have a network of size n, then calculating the number of triangles that are in that network takes on the order of n cubed. Sorry, that should say n raised to the third. Can take of the order n to the third computational time, and that's just too much for a large model or for a large network. So I gave this a lot of thought and wanted to figure out how can we do this in a way to where we get similar interpretation out of a method. And so we introduced, therefore, a sampling-based PCAN method. I called it SPCAN. Maybe I should have called it PCANs. Method, which divides the network into a partition first and calculates counts on each subnetwork and then averages across the samples. And so let me walk you through that really quickly. So the sampling-based method is, instead of calculating these statistics on the entire graph in this sequence of graphs, we're instead going to partition randomly each one of the graphs within the sequence, we're within the collection, into capital K different disjoint subnetworks. And then once we do that, we'll run the same process. So we're going to calculate the summary statistics on each one of these smaller networks. So you can imagine if you have an incredibly large network of size, say, 1 million, if you broke this down into, say, 1,000 subnetworks, then you're greatly diminishing the size or the computational lift for calculating things like triangles. And so it can be very useful in that situation when you have incredibly large graphs. And the idea there again is now we're going to average instead of just using the single PCs that we were before. So for each observation GI in the sequence, we can average over the subnetworks to obtain P by 1 mean subgraph density vector. So here we're getting an SI bar, which is just going to be the average over the subnetworks for that statistic. And at the end of the day, what you end up getting is this P by N mean subgraph density matrix. So here, capital M is our mean subgraph density. So before we just had a single subgraph density matrix. Here we have a mean subgraph density matrix where we're averaging over the partition. And then we go through and run the same, PCA on now capital N. Okay, so why is this interesting? For one, it actually provides a way that we can naturally run PCA and get something interpretable out of a sample of networks. So that's already, in my opinion, very interesting and useful. The other thing that makes this very interesting is actually very recent theory, and this is also in the paper that's currently a preprint, but very recent kind of central limit theory on a large suite of network models for these subgraph statistics. And so in particular, what I wanted to look at was investigating the statistical properties of both the SPCAN and PCAN under a regime of what's called the kernel-based random graph model. And here, just to give an overview, essentially we found three things. So one is that the embeddings from SPCAN and PCAN are asymptotically equivalent in expectation. Two, the mean subgraph density matrix M is asymptotically normal, as you may expect, as the number of samples grows to infinity. And then three, the sample eigenvalues and eigenvectors from the SPCAN algorithm are asymptotically normal. And there's more details in the paper, but I also want to continue on here just to give you a little bit of the ideas of the statements. So first, and I think this is really for those that are interested in network theory and thinking about probabilistic random graphs, this is an incredibly useful and well understood exchangeable graph called I'm calling it the kernel-based random graph. It's been called that as well. A lot of folks just refer to this as the random graph of Lavache 2012. So this was in a really large text of random graph theory by Lavache. But the kernel-based random graph is generated in the following way. So if you let N be a sequence, be a set of nodes, and F just be a continuous function on 0 to 1 by 0 to 1 to 0 to 1, then define, so just on the unit square to the unit interval, then let G be the probability distribution over all graphs with vertex set N and edge set E. Then if we just create a feature Xi for every node, which is a uniform, and we're independently doing this, is a uniform 0 to 1, then we create the graph by conditionally forming edges using that X, and we form edges with probability Pij forms an edge, so there's an edge between I and J, given Xi and Xj equal to this F of Xi Xj. So if you create what's called a kernel, just this function F, then what we say is you take Xi to be uniform 0, 1, and then create a graph based on this probability structure based on F. Then we say that G is a kernel-based random graph with kernel F if G satisfies 1 and 2. And in general, I'll just write G is distributed as this kind of kernel-based function. But what you'll notice is this is an incredibly large family of graphs. You can essentially create a continuous function. If you can write a continuous function from F, and then from there we can start to actually develop these kernel-based random graphs. So there's a lot of opportunity here to play around with this graph style, and in particular, the latent space model can be created using this same style of graph. So it's quite a large family of graphs that are possible here. And now if we look at the relationships between PCAN and SPCAN, so for time, I'm just going to quickly go through this. The basic idea is that we need to make sure there's a constraint on how many features, on how many nodes are in any of the configurations you're interested in. So when we go through the entire sequence and create this vector of configurations, F1 through FP, so say that's squares, triangles, etc., then we need to make sure that the size of the largest configuration is half the size of the minimum network in the collection. So basically, if you have a network of size 100, then none of the features can be above size 50, say, which is reasonable when we're thinking about these kind of local motifs and characteristics of a network. And then if GI, so the main crux of the idea here is if GI is a kernel-based random graph for each one of the graphs in the collection, then we can say for fixed P less than N, so whenever we have fewer features than we do overall samples, then we have equality and expectation of M and S. So this is with SPCAN as well and PCAN. And for all L, then we have almost sure convergence of the eigenvalues and eigenvectors to the same, what we expect under the PCAN algorithm. So we have asymptotic equivalence here. And furthermore, and I won't go through the details of all of this. I know I gave you all the writing, but basically what I want to say is under very light assumptions here, we can essentially show that there's a central limit theorem for subgraph densities. And this was very recent, and we had to apply it to our particular situation where we're looking at subgraphs over a sample and construct this in an appropriate way. But the basic idea is that if you're looking at the mean across a subgraph configuration and take its real mean, which is the value of, or the expected value of the kernel function under the kernel graph model, then we get a central limit theorem for each one of the entries of M. So basically this is saying that the subgraph densities, when we take this average subgraph density, we get a central limit theorem that's based, has an asymptotic distribution of a normal with mean 0, and here variance covariance matrix depending on the size of the networks, what the kernel function is, and then this capital FP, so the features that you determine. And that then allows us to actually look at a central limit theorem for the PCs from SPCAN. So we can actually get normality, also central limit theorems, and derive them for the eigenvalues and eigenvectors of what's coming from SPCAN as well. The whole point of why I wanted to bring this up, one, it gives us an understanding at a distributional level of what's going on with these features. That's in addition to what we already have for kind of interpretation that we've talked about so far. But moreover, you can actually use testing, hypothesis testing here with these central limit theorems to understand differences between two samples. So if you have two samples of which you run this SPCAN method, then we can actually start to compare the PCs that are output using a t-test essentially with appropriate test statistics that we can draw from these asymptotic distributions. And that has not been done thus far for these kind of feature analyses within a graph or within samples of a graph in particular. So kind of fun, something fun to think about, and we can actually gain inference out of these features and interpretability. So now I know I'm going to go until about 4:50 or so. Is that right? If that's okay. Just can someone give me a thumbs up? I just want to make sure I'm going on time. About 10 minutes left. All right, I'll assume 10 minutes and we'll go from there.
That'd be good.
Okay, great. so perfect. Okay, so applications. So what, is this useful in practice? So I motivated this the work here with functional connectivity. So let's return to a problem in functional connectivity. Here I'm actually going to look at fMRI that was obtained for a group of 72 healthy controls and 50 patients with schizophrenia. This was publicly available data. I'm happy to share it if anybody wants to also investigate this data. I've looked at it several times to best understand what's going on in their networks. I ran PCAN and investigated the top principal components. The goal was really to explore the variability explained in the sample, as well as to classify between healthy and patient groups. And I just want to point out, I think this is actually very interesting. From a network analysis standpoint, I've seen a lot about, and I kind of alluded to this earlier, a lot about mean characteristics in a graph, but very little about variability of the graphs themselves. And I think it's a hard thing to try to really quantify. So I'm excited that this PCA is actually offering us a way, that PCA for networks is actually offering us a way to understand the variability explained in networks as well. And there's a lot of powerful results we can get out of this. So this is just an example to show, if you look at the average connectivity between, the healthy and patient groups, so healthy on the left, patient on the right, and nodes are colored by the same statistics, so these aren't exactly oriented correctly. But what you can see just very quickly, anyway, at a glance, is they're quite a bit different. There are differences here. The clustering structure is different. You'll see with dark blue, for example, here, like this bluish purplish color does not have such an interesting cluster on the right-hand side. These are connected. The light blue, I think this is actually the default mode network, I'll talk about in a second, is connected with pink. And this is connected with pink, red, and blue over here. Point is, there's a lot of connectivity differences in the average. And so I want to explore that a little bit more, but first I want to do a quick digression into just stating, when we're analyzing functional connectivity matrices, very often we break it down according to what are called functional subnetworks of the brain. And the way to think about that is, if we have a network representing the functional connectivity, then each one, or regions, actual regions that we can identify in the brain, spatial locations, are responsible for different functions of a person. So here's an example, kind of a toy example or picture of what happens. So you can imagine this area being mostly responsible for hearing, speech, and so on. And so there are well quantified functional subnetworks that are understood. And we often will use that in functional connectivity analysis to best kind of portray what's happening in different regions. And then that can be tied to actual different functions of the brain for the given person. So I do that. And in the analysis, I go through looking at subgraph configurations, including isolates, which are just nodes that are by themselves, edges, K-stars, and cycles. I do a whole brain analysis, which is just taking the entire network and running PCAN on the data set on the entire brain. And I also do a subnetwork analysis where I break the network now, the whole brain, down into functional subnetworks, from which I do the analysis separately. And so I ran PCAN on these and tested the effect, both of the effective and predictive power of PCs via logistic regression. And here we can start to look at, standard scree plots and plots that everybody has seen going through PCA, and start to now look at this according to variability explained in each one of these networks. And so what's really interesting is, in general, so if we're just looking at, these are now the PCs for healthy controls. If we look at the whole brain, default mode, and salience network, so these are two of the functional subnetworks we're looking at, you get a picture of what's happening. The first PC, by and large, is explaining most of the variability. So roughly 85%, somewhere between 80 and 87%. The second PC explains roughly 10%. The third PC is somewhere between 2 and 5%. And then from then on out, everything's below 1%. So it's kind of the first three PCs that are really telling us, explaining the most variability in these networks. But more than that is the fact that the first PC is by and large capturing the most variability. We can do this, of course, we can actually break this down according to the top contributors to each one of these PCs as well. So we can look at, for example, we looked at some of the networks where we actually started to see differences. We've got whole brain network, hand network, and salience network. And if you start to look at this, these now on the y-axis are contributions, so relative contributions of each one of these statistics. So for the first PC on the left, second PC, third, fourth, first, second, third, and so on. And so we do that for each one of these subnetwork analyses and the whole brain. And we can start to compare actually how these statistics are differing in their contributions to the PCs. And so here we found, by and large, there were differences between the second and third PCs of the whole brain versus hand and salience. There was consistency between hand and salience. And we find that indeed higher order PCs, so once you go to the second or third PC, beyond the first one, are actually most predictive of schizophrenia versus healthy. And this is actually quite interesting. So I want to point out the reason why we need to think about these kinds of things. So the strongest signal, so now here's what I'm giving in this table are just showing the top three PCs, the overall variability explained, as well as what you can imagine is its significance in a logistic regression, so if we ran logistic regression on the PCs for every individual, so what effect did each one of these PCs have on helping predict schizophrenia in healthy? So this is kind of the effect for discriminating between these two groups. And what's interesting is the hand and the salience network showed that PC2 and PC3 were significant here, or significant at 0.1 level, so weakly significant. But the interesting thing there is that there's actually more help, I guess, or more effect from PC2 and 3, which explain only about 13 or 14% of the variability, but that's actually where we start to see some differentiation between these groups. And that's helpful because what that helps people understand is to say, well, look, we don't need to just look at the top level summaries of these networks to understand differences between these patient groups. This is by and large what's done today. So people calculate these statistics and just run t-tests and say, look, they're different or not. Here, what I'm suggesting, what these results are suggesting, is actually that we go further than that and look at higher dimensions. So things that don't just explain this higher level variability, but we need to go to PC2 or 3 to be able to say something. And indeed, when we actually do predictive analysis of these networks, so if we think about the logistic regression for identifying schizophrenia from healthy, then I ran 5 different methods here where we have PCAN that was for the whole brain analysis, PCAN of combining all of the subnetwork PCs, subnetwork PCAN with ridge regression, so to do a regularization. And then we actually just put in the raw configurations as well. So if we, instead of running PCA on the configurations like what we did with PCAN, we just looked at the subgraph densities themselves, then you can see the differences in predictive ability. And it turns out that by using subnetworks and PCAN on all of the subnetworks, we get the best predictive performance. And this was true across accuracy, sensitivity, and specificity as well. So I only have 1 minute left, so I won't go into this example. There's another really fun example of polarization in US Congress. And the moral of the story here is that we are polarized, and PCAN can certainly identify that and identify it in the first PC. I'll leave it at that. But basically, by looking at congressional agreements in Congress, so based on votes for bills that go to the Senate, we can actually see a very clear division if we look at the PCs of these statistics within a time course of all of the Congresses from, what was it, 1975 up until 2013. Kind of interesting, but it showed up in the first PC. In fact, we see that it explains 89%, and the AUC was approximately 0.985. So it was insanely easy to predict with something like PCAN. Much less complicated and complex problem. You might expect that from political polarization these days. Okay, so I'll end with the following. What's next? I really want to take this and start thinking about network models based on the principal components that we've identified. So they were based on some random graph models like the ERGM and the kernel-based random graph model. But now, how can we take these PCs and do something like principal component regression? In particular, we can actually use these PCs from the PCAN method as features or variables in the exponential random graph model. And what I believe, and I'm working on showing this, avoid issues of collinearity and problems that are inherent to the ERGM up front. Furthermore, representation of dynamic and other dependent network samples and applications of PCs and these kinds of features for change point detection as well in the sequence of graphs. Okay, I'll end there. Thank you so much for having me again. I really appreciate it, and I hope you enjoyed the talk. And here's kind of some links for publicly available code, my email, as well as a preprint, if you'd like to ask me anything.
Okay, let's have a few questions. Anyone has any questions? Just speak up.
James, I've got a question.
Sure.
Is there any way, I'm thinking about trying to classify whether towns in the US have the same temperatures. And so if I compute a correlation coefficient, which is between -1 and +1 instead of 0 and 1, is there any way to use a graph analysis of that to tell me what towns are like each other or not?
The short answer is yes. I feel like I can always apply networks to.
So what would you do? Just take absolute values or something? Correlation? Or?
Actually, there's a few things. I guess one is if you're looking for towns that have similar, are you looking at similar ups and downs, like they go up with each other and down with each other? So it's similar pairwise trends, or are you looking at just similar magnitude?
No, actually, what's really valuable to the meteorologists are towns that have what they call so-called teleconnections, which is negative correlations where they're far apart, but you can tell me that the Southeast is going to be cold because Alaska is warm, these type of things.
I see. Yeah. No, that's great. So yes, we can certainly do an analysis there, a network analysis, and in fact use these, kinds of, well, you could imagine some form of clustering, right? So community detection or otherwise for those different towns. The first question I think of identifying these kind of communities that are similar, with large negative correlations, I would actually use something like community detection on there's actually methods for correlation networks, so you could directly do that.
Okay.
Mm-hmm. I'm happy to. I'll send you some more info on that. Yeah, there's some available methods for that as well. That'd be fun to see.
Yeah.
Oh yeah.
Fangye.
Hello, can you hear me? Yeah. Well, hi James. Thanks for the nice talk. I'm quite interested in the network analysis. So I have 3 questions. The first is about your applications. So for the different, you treat different subgroups of the brain data separately and apply your model to different sorts of data, right? So you don't assume there is connection between each part of the brain, right?
So I did, that's a great question. So I did both, where the first thing was the whole brain analysis, where it's using all information. So we're doing I'll call it between functional subnetwork and within. The secondary analysis, you're right, I was looking at subnetworks within the graph and not connections between them. So that's true. I mean, it'd be interesting also to bring in the kind of inner connections as well.
Okay, cool. Yeah, and also my other 2 questions is about how we compute the PCA. I see your steps, you first have some summary statistics, they are counts, right? And then you do some normalization. So basically it means you're doing PCA to some compositional data, right? So do they already have some correlation inside, because maybe they sum to 1 or they are between 0 and 1? So will that affect your final, I don't know, your final results? Yeah.
So let's see. So the matrix that we're running this on is the P, which P is representing the number of features or the configurations that you're putting into the model, by capital N, which are the number of graphs. These represent each graph in the sample. So G1, G2, G3, and so on up to Gn. The features themselves very well could have correlation, right? So that's absolutely. And in fact, that's kind of a major point of where I want to take this and apply it to something like PC regression for networks, because it's very often the case that people just kind of run these and don't think about that correlation, right?
Okay.
So having said that, so for each feature, the entries there are the network or the subgraph density. So it's a number between 0 and 1. So how often did it occur in the network divided by the total possible numbers that could have occurred that given configuration. And then the matrix itself is scaled as usually done. I didn't give, I guess I did say here, mean centered subgraph density matrix. So I do end up, scaling to have it mean centered before running PCA as well. Does that make sense? Or
yeah, it makes sense. And my last question is more about like networks. Why? So since like we're using like PCA, it's more using like correlation matrix, right? Do PCA based on like covariance or correlation matrix. So I think like usually like graphical models are more interested in like the precision matrix, right? Or can you tell us like more about like when we are more interested in like correlation matrix and when we are more interested in the precision matrix? Okay, thank you.
Yeah, great question. So there's a really interesting, there's kind of two parts to what I like to see as like the overall network spectrum. So the first is often called graphical models, right? So that's the realm of we have data that has dependence of some kind, and we end up estimating the precision matrix, right? For something like a Gaussian graphical model, as an example. And there's other types, right? So Poisson graphical models and so on. The aim there is to estimate what is the best graph, right? So what is the graph that represents this? So by all means, you could use it, and it's a causal graph, right? So this has a causal representation as well. So that very well could be a way of saying, okay, we have all of these time series, let's run graphical models to get the graph. Actually, at the end of the day, I'll just give a comment there and say the method in general is for any sample of graphs. Like it doesn't matter how you got the sample. I'll only say in general in functional connectivity, people are using things like correlations and not partial or not the graphical model strategy. I wouldn't say that's the best idea. I would actually say, the causal inference is maybe, is much more, I think, useful here. But I think there can be differences, right? So one's more associative where the other is more causal in nature. With the causal representations, you often get a much more sparse network, which can make things more challenging for analysis as well.
Okay, cool. Yeah, thank you. Yeah,
thank you.
That's good. Nice talk.
Thanks. Oh yeah, Robert.
Yeah, I only want to ask if someone else doesn't have a question. Okay. The central limit theorem, I was amazed to see that and that somebody actually worked that out. Is there an explicit form for those covariance matrices or?
Yes,
Really?
There is. It's nasty. I did not write it out.
Yeah, I noticed.
Yeah,
and that's how you got the p-values.
Yes, that's correct. So you can actually get these. You can actually get p-values from this.
Who did that? That
was Maugis. Maugis. He's now in tech, but he wrote a paper with Kerry Priebe. So there was an earlier paper. This is very based on looking at subgraph configurations, and they proved the central limit theory for these subgraph configurations. It was a pretty cool result. Really useful.
Yeah. Okay. Thanks.
I'll send you the paper. It's nice.
All right.
Awesome. Well, thanks so much, everybody. I really appreciate your time. And, like I said, if you have any questions, send me an email. I'm happy to share these slides too, if anybody wants to see them for later.
Thanks, James.
Thank you.
So, okay, we will stop here and see you.
All right. Take care.